Hi, welcome back to physics. We're studying waves today, which, as you know, are disturbances caused by particles in a medium vibrating to send energy across that medium without themselves moving. Recently, we've learned about something called the superposition principle, which is the idea that multiple waves can occupy the same space at the same time. And when that happens, it's something called interference. Interference is actually going to play a pretty large part in what we do today. Because look at this thing. Now, what's that? What's going on here? This doesn't really look like the waves we've seen before, does it? Waves are kind of all about motion, but this one, I mean, there's like wiggling, but I don't really see this thing really moving anywhere. The peaks, the crests and troughs, they just kind of sit there. This is what we call a standing wave. This is an interesting phenomenon that comes up. This is actually the basis behind literally every musical instrument that exists. The idea of a standing wave is that you have two waves going on at the same time, with the same frequency and the same amplitude, moving in opposite directions of each other. The way they interfere with each other is unique, and that interference pattern is called a standing wave. Some terminology that you should know for these. If you notice, there's a piece of that wave that just kind of doesn't go anywhere. There's no motion, no amplitude, it just sort of sits still. That spot of no motion is called a node. There's typically a node at either end, although not always. And there may be more than one in the center. You have to identify what's going on in the wave to determine that. In between the nodes, you have these spots where there's lots of motion, a crest or a trough. This pieces of the wave that are going up and down rapidly. Those are called antinodes. That's the part that moves the most. So what's the deal? How does this work? Well, first of all, these waves can only fit in certain spaces. So you get certain wavelengths depending on the environment that you're in. So say this person's holding on to a jump rope that's attached to the wall. So the largest wave that you can possibly make would be where between the hand and the wall, the rope just goes up, then down, then up, then down, then up, then down. That is the largest wave possible to fit in the space, and it's actually only one half the wave is visible at any one time. Fit in between the hand and the wall is one half of the total wavelength. If you think about a wave being an up part combined with a down part, or one full sine curve, you can see that you can only really ever have a half in there at once. If you change the frequency, you can get a smaller wave to fit in there. And so here's an example where there are two pieces to this wave, one up part and one down part. As I just said, that's going to be one full wavelength. So between the hand and the wall is lambda, one wavelength. One waveform, one full sine curve, the up and the down part as well. And if you change the frequency again, you can't have any old standing wave fit in here, but you can have one of 1.5 times the wavelength here. So you can see from the hand going towards the wall, you go up once and down once. That's one full wavelength. And then one more up part before you return to the last node at the wall. So that's 1.5 full wavelengths fit in there. And you can go up from there. If you have smaller and smaller and smaller wavelengths, you can fit more and more and more of them within there. But it needs to be full amounts. This screen is showing a bit of where these pieces come from. Let's take this wave apart. So there's two dots displayed here and two waves. The top wave moving one direction, the bottom wave moving the other. And the standing wave, the actual physical thing that's going on, is the dark line at the bottom. The first dot is showing where nodes come from. The idea that that piece of the material, that piece of the medium, is at a spot that happens to be always experiencing destructive interference. That at any moment in time, if one of those two waves is going up, the other one's going down, or vice versa, there's always full cancellation. And it becomes a node because the amplitude is always 0. It's interesting. The antinodes, by contrast, which are between them, are 90 degrees out of phase. And what that means is that anytime one of those two waves has a positive amplitude or is going up, so is the other one. So they're always going to be building on each other. If the first wave is going down, so is the other one. It'll be going into a trough. And so with this constructive interference always happening at that point, the amplitudes are very large. There's lots of motion. The antinodes go way up, way down, way up, way down, larger than the original waves were. And that's the gist of how you create a standing wave. So that's something you should know about. The second piece I wanted to look at today is something called the Doppler effect, which I'm sure you've heard of before. The Doppler effect is about motion, but not the kind of motion like we've seen before where the waves are moving from place to place or something. Doppler effects come about when you either have the source of a wave being in motion or the observer of the wave being in motion. When that happens, you experience a frequency shift or a frequency change. The most common example of this is, well, just stand on the side of the road. You can listen to the cars go by. The pitch that you hear of a moving car is different if it's coming towards you versus if it's going away. Let's take a closer look at how that works. So this first example here is where you have two observers, a stationary boy behind the car and a stationary dog in front of it. They're going to hear different sounds from each other. The idea is this. As those waves are emitted by the car moves between one wavefront and the next, so not all of them are centered at the same position. The waves that were emitted earlier are bigger and set further back. The newer waves are further forward, and effectively that means they're going to kind of bunch up in front of the car. You can kind of see that in this picture. On the dog side of it, where the car is sort of chasing its own waves, the wavelengths themselves are going to shrink to be smaller, but the frequencies are going to go up to match. So the dog will hear a higher pitch frequency being in front of the car. The boy in the back sees those wavelengths stretched out much longer, which is going to decrease the frequency, which means the pitch that he hears will be different. It will be lower. The same effect can happen if the source of the sound is stationary, but the observer is moving. So here we've got a siren playing a tone, and the motorcyclist driving towards it on one side is going to hear a higher frequency sound. So now those sound waves which are visible, those wavefronts, are evenly spaced, all the same frequency, all the same wavelength. But to that observer, as you drive towards it, you're going to cross over more wavefronts in any given amount of time. In 1 second, instead of hitting 50, you'll hit 60. You're going to see them more frequently or with a higher frequency. Similarly, once you pass by the source of the sound and are now moving away from it, you're chasing those waves. It's going to take you longer to catch up to successive wavefronts, which means you'll hear them with less frequency. That means the pitch will go down, and that's the change in pitch due to a moving observer and a stationary source. To wrap it up for today, let's take a look at a few examples. In motion, first you have a stationary source of sound just sitting there in the room emitting some noise, and these concentric circles are showing that all of those wavelengths and frequencies are going to be kind of just the same as those waves go outward in all directions at the same rate. Fine. So far so good. What if we start moving? So now this moving source is emitting sound waves, but the earlier waves are positioned differently than the later ones. And again, like we saw in the earlier example, you see this bunching up on the right-hand side as the source of the sound chases its own sound waves. Now this object isn't moving all that fast. It's under Mach 1, and the Mach number of something is basically how does its speed compare to the speed of sound. So what if we speed up? Now we're moving at the speed of sound. This is Mach 1. And you can see that this source of sound is keeping up with the sound waves that it has already created, which means you won't hear it until it's right there next to you, and then you're going to hear a whole bunch of sound all at once with a very high frequency, because basically all those waves are going to come in almost all at once. And if you speed up just a little bit more, so that you're now going faster than the sound that you're making, well, an observer standing nearby won't hear anything until you're well past them. And what do they hear then? Notice the further this object moves, you see this angle being built up, a kind of a triangle shape with the object at the point. What's happening there is all of those wavefronts are coming in at the same place. All along that angle, you have every bit of sound from the whole journey all piling together and constructively interfering with each other. So you don't hear anything, you don't hear anything, you don't hear anything until that angled line sweeps across you and you get all of the sound all at once, all constructively interfered together to make one humongous wave called a sonic boom. And that's where those come from. So that's a bit about standing waves and the Doppler effect, and a couple of the ways we'll see that going through. Thanks for listening today. I'll see you next time.